medical community. I'm thinking off the top of my head, how about next month's meeting?
Okay. Hi, everyone. I've just started the recording. I'm Susan Murray. I'm hoping that you can't hear me.
No, I can hear you, but often I hear recording has begun. When you,
Oh, well,
I'm just asking.
Well, Susan should have her
I think
volume muted.
I did have it muted. I think it's fine.
Okay,
It did suggest I was recording.
perfect. Sorry.
So, I'm Susan Murray. I'm right now I'm helping run the Ann Arbor ASA along with, these fellows over here. And we have this meeting about once a month unless there's a good reason not to, like ENAR or Thanksgiving or Christmas. It's always the last Tuesday of the month. And I usually try to get this room. So everyone here is welcome. I also do a lot of arm twisting to get good speakers. And so everyone who speaks here is a good sport and a good speaker both. Next month, we're going to have Malcolm Risk, and he's going to, I'll advertise his talk as soon as he tells me what he's talking about. This month, I'm quite happy to introduce Swaraj Bose, who I think is everyone here knows. And he is a PhD student in the Department of Biostatistics in our own University of Michigan. And he is working on a dissertation that builds causal inference methods for micro-randomized trials, which is one of the more modern kind of clinical trials to try to figure out with all of this wearable data. And to create tools to better understand individual level causal effects using conformal inference techniques. So we'll look forward to figuring out what that is. Swaraj collaborates extensively with the pulmonary critical care internal medicine faculty at the University of Michigan and is involved in many projects to further pulmonary fibrosis, COPD, and lung cancer research. And on a personal note, he's just a wonderful human being. So please join me in welcoming Swaraj. I'm really looking forward to hearing finally what you're doing.
Okay. I'm Barry DeSico. I run the Ann Arbor, our users group on Meetup. We meet on the second Thursday of the month. The next meeting will be covered time series plot. So you can look for us on Meetup and come over. We also have free pizzas. Thank you. Sorry to interrupt.
Yeah, thank you, Susan, for the very nice introduction. Yeah, I look forward to presenting my.
You want to just grab that?
I see it on the computer.
Just grab the. We are good at problem solving. And I think all it's is I keep on having to refresh this stuff. So, nobody panic. That work? No. Okay, nobody panic because,
No, we can see it on the screen. The computer.
well, the people in the room who came in live should be rewarded by actually seeing the talk. But if I turn this on again, it'll pop back up. Let's just see what happens with single screen. I was really trying to avoid being on this camera. It says it's warming up. Might be the owl thing. It might be that thing. Touch screen.
Yeah. Look at you.
Wait, I don't know what I did, so I don't take any credit, but let's get the little thing down. Be civilized to not have lines in the middle of our slides. All right, now, as long as no one blows on anything, I think we're good.
Yay, tech support.
I'm good. I'm hoping everyone can hear me. Okay. Yeah, so I'm going to present this work, which is supervision of my PhD advisor of the Arbor. It's regarding building prediction intervals for individual treatment effects in a time varying framework. And I've organized the presentation so that we go through all the things we need to know before I implement it. And yeah, I'll give a bunch of background motivation and then I'll go into my. So let's start. I'll start with our motivating section. Yeah, so I'll start with our motivating setting, which is yes.
I can't hear you well at all, so I think, yeah, use the microphone. You can probably pick any of those. Switch on.
Hello. Okay. Yeah. So yeah, let's start with our motivating setting, which is micro-randomized trials. As the name suggests, it's a sort of randomized trial where enrolled individuals are randomized to treatment on numerous occasions. This can be up to thousands of occasions depending on the micro-randomized trial. We assume this kind of a data structure where we have individuals 1 through capital N indexed by I, and we have time points or decision points 1 through capital T indexed by J. In these sorts of trials where you have time varying effects and treatment effects which vary a lot, or even on the individual level, some sort of idea about these treatment effects for different individuals would help personalize treatment assignment and enhance decision making. So that's kind of why we want to know about individual level effects. So before I introduce our estimate of interest, I'd like to start by introducing some concepts and some notation. So first, we have the binary treatment at decision point or time point J for individual I, and it can take two values, 0 or 1, depending on whether treatment was administered or not. We also have the corresponding potential outcomes for that individual at that time point, given by Yij, Aij bar, comma 0, and Yij, Aij bar, comma 1, where Aij bar is the sequence of treatments that the person or the individual received before time point J. And Xij we can think of as covariates or historically observed information that might include past actions or past treatments as well. And finally, we have the propensity score, which is the conditional probability of treatment assignment at time point J for individual I, which is given by pi. This brings us to the fundamental problem of causal inference, which is that we never observe counterfactuals. Our observed outcome is either one of the potential outcomes, and thus we can write the observed outcome as a combination of both potential outcomes, but note that we only observe one of them. So if Aij was 1, we would observe the first term, which is this one. And if Aij was 0, we would observe this term, which is, so we only observe one of the potential outcomes.
May I ask?
Yes.
What-
Go ahead.
The bar over the A represents the sequence of.
The sequence of treatments.
And then the
yeah.
A is just the next.
Correct. Yeah. Yeah, as motivated before, knowing about these effects on an individual level is useful and helpful. And we define the individual treatment effect to be the difference of our potential outcomes at time point J for an individual I. And our goal is to build a prediction interval at time point J for let's say we have a new person, I, at a decision point J. Our goal is to build this prediction interval that will contain the true ITE, or the individual treatment effect, with a probability that's greater than equal to 1 minus alpha for some pre-specified miscoverage rate alpha. Yeah, so what the probability statement basically is saying is that the true ITE will lie in the prediction interval with a probability of at least 1 minus alpha, where alpha is pre-specified. So this is what we are trying to accomplish. And as I said before, knowledge about these individual level effects can be very helpful in personalized medicine, or it can also be used as moderators to improve estimation of treatment effects as a whole. So the two key ideas that I'll go through before I go into the method is pseudo outcome regression. And I have a detailed slide about this next, but the overarching idea is that since we never observe counterfactuals, it's very hard to build prediction intervals for something that you don't observe. So what pseudo outcome regression does is that it helps us build these pseudo outcomes, which are kind of mimicking what the true ITE might be like. And then based on those pseudo outcomes, we create prediction intervals for our unobserved ITE. And the second key idea that we're going to utilize is that of conformal predictions. And that is basically a machine learning framework, which gives us valid finite sample guarantees without assuming any sort of model or distribution that we need for that. So going right into pseudo outcome regression, let's say we have the data xij, aij, yij. We can convert that into a tuple instead of a triplet. So the tuple will include xij and y tilde phi of ij. So this is basically our pseudo outcome. And to get this, we can use widely used meta learners. One of the examples is the doubly robust learner, as I'm sure a lot of you have seen before. This is the equation for that. And I just want to point out that the reason for using the doubly robust learner is that we have two attempts to get at what we want to, like we have two situations in which case this provides valid inference. The first case is if we have a known propensity score, which is like it's known by default, since MRTs is a design where you know the propensity score by default. So this is very useful for us. The other way that you can get it, even though if you don't know the propensity score, is if you have correctly specified outcome, like conditional outcome models. So that's why doubly robust learner is a very good choice for building pseudo outcomes. Yes, so these are the conditional average outcomes, and we plug in the estimates here to get the doubly robust learner, meta learner pseudo outcomes. And then the idea is after we get these, like we've converted our data into these pairs, we build prediction intervals for these pseudo outcomes, and then we claim that the true ITE is going to lie in these created intervals.
Question?
Yes.
Can you talk a little bit about what a pseudo outcome is, or is that beyond the scope of this talk?
So very intuitively speaking, like in this case, we want to build a pseudo outcome because if we consider a regression setup, right? So we have a y and an x, and we are trying to figure out how y is related to x. But in the ITE setup, since we only observe one of the potential outcomes, not both, we really don't have like something to regress on, for instance. So we need to build these pseudo outcomes which will mimic the true ITE. And then we are trying to suggest that, okay, like based on these pseudo outcomes, the intervals we create are going to cover the actual ITE.
Does the pseudo outcomes include the counterfactual?
Yeah.
Okay.
Yeah.
Okay.
So the pseudo outcomes will contain the observed outcome, which is either one of the counterfactuals based on if they receive treatment or not. So yeah, it's a function of the observed outcome.
Thanks.
And the second key idea is that of conformal predictions. It's a really cool idea and it appealed to me a lot, which is why probably I'm doing research in this area. But it's basically a model and distribution free framework. It allows us to quantify uncertainty related to black box or sophisticated machine learning models, which is really sweet. And it gives us finite sample validity, which is also very nice. The only key assumption that they use is that the data is IID or exchangeable. Exchangeable data is kind of a weaker assumption than IID. Exchangeability, IID implies exchangeability, but exchangeability does not always imply IID. You can still have some sort of a dependence in the data, but it's kind of close, like you can think of it as kind of IID, but with certain dependent structures. So this is, just a second. Yeah, so to go over how conformal predictions work in general, let's take a step back and go to our general regression setting where we have data X and Y. So X are our covariates and Y is the outcome. It's not the potential outcomes framework. It's just a normal regression setup. So the way it works is you first split your training data into a modeling data set and a calibration data set. And then based on this modeling data set, we are trying to estimate the function f, which gives us, so we are trying to estimate this function f, and that can be done using any complicated machine learning model, or as simple as linear regression. And now based on this estimated f, we can get predictions for y in our calibration data. Let's call these y hat. And now since calibration data is part of the training data, we can get some sort of conformity score. We can think of these as absolute residuals in this case. So this gives us some sort of idea about what kind of errors we are making when we are doing predictions. And then in the simple regression case, we just calculate the quantile, the 1 minus alpha quantile of the empirical, 1 minus alpha empirical quantile of the distribution of conformity scores that we have. And based on this, we are going to create this prediction interval that is for a test data point X test, which is the estimate plus minus this quantile. And this is like the very basic conformal prediction setup. There are many complicated things which you can do in every one of these boxes. But to give a very basic idea of how the algorithm works, I think, yeah, this is a pretty good idea of what goes on in the background. And so this is for if you have like a mean estimator and then you're adding and subtracting something else from it. What we could also do, instead of having a mean estimator, we could have quantile estimators, so the only change here is that we have quantile estimators instead of the mean estimator. And what that helps is that it gives us the endpoints of the interval instead of giving us a mean estimator. So let's say we have two quantile regressors, Q hat low and Q hat high. You can think of these as the start point and the end point of the prediction interval. And again, for these, you can use any sort of complicated machine learning models. And then similarly, you get predictions for the interval. And then you calculate a conformity score, which used to be an absolute residual in the previous slide. But here, since we have an interval, it's slightly more complicated. It's the max of this equation here. What I want to point out is that this conformity score is very useful because it penalizes both overcoverage and undercoverage. So if you notice that if y is actually inside the interval that we have constructed using these two estimates, it is going to, this v is going to take a negative score. So in the situation where all of our created intervals are actually covering y, all of these conformity scores are going to be negative, which means that the final prediction interval, which uses the quantile from this distribution, is going to shrink and is going to give us a better estimate or a better interval than what we would get using just quantile regression. And this also obviously accounts for undercoverage. So if y lies out on either side, then we get a positive score. So in that case, it will widen our interval so that we have the guarantees that we want of covering it with 1 minus alpha coverage. So the conformalized quantile regression framework is something that we are going to use in our method. And I believe we have, yeah, go ahead.
When you're doing this, and then the first slide before quantile, does that rely on having a continuous outcome?
Yes,
Okay.
yeah,
All right.
yeah, absolutely, yeah. Yeah, now going into our method, these assumptions are very standard in causal inference. We assume positivity, which means that the propensity score pi is strictly positive. We assume consistency, which means that the outcome that we observe is equal to one of the potential outcomes. We also assume sequential ignorability, which means that there's no hidden there's no hidden confounding, essentially. And then we also assume a known propensity score, which is not a restrictive assumption because, again, this is satisfied by design in an MRT, which is our motivating setting. And in the past, people have constructed prediction intervals for cross-sectional ITEs, and they've assumed exchangeable data. But in our case, since we are operating in an MRT framework, like most of these outcomes are going to be highly correlated. So we can't really assume exchangeability. So the novelty arises because we are doing A, longitudinal instead of cross-sectional, and then we have to drop the assumption of exchangeability. So those are the two things that we are going to address. So the first step of our method is data splitting. In our case, we need 3 instead of the 2. We need 3 splits of the data, as you can see. With the first split of the data, we estimate our nuisance functions, which is the propensity score and the conditional average models. We assume that the propensity score is known, so we are essentially estimating just the 2 conditional average models. And then based on these estimates, in the next step, we are going to create these pseudo outcomes for our modeling and our calibration dataset. And then once we have these pseudo outcomes using the modeling dataset, we are going to fit quantile regression models. And this is, again, relying on the idea of CQR, as I introduced a few slides ago. Now, once we have these quantile estimates, we are going to find the conformity scores. Based on we are going to first predict the upper and the lower quantiles, and then we are going to calculate the conformity scores given by the same equation that we saw before. The only difference is that we have pseudo outcomes here. And then finally, we are going to assign some weights, which I will talk about in detail later. But let's assume for now that we have these weights and we are assigning them to each and every point in the calibration dataset for these V5s. And we are going to build this prediction interval for this new point xij, which is going to calibrate the lower and the upper quantiles that we predicted by this weighted quantile from the empirical distribution of V5s.
Where do the weights arise again?
So I'll go into the weights later, but for now, let's assume that for each and every data point that we have in the calibration dataset, we have some weight that goes with them. Yeah, and to motivate the weights, I promised Susan that I would not have too much theory, but we have to have a bit for motivation. I apologize, but yeah. So the first theorem, essentially, like I just want to focus on the takeaway, and the weights arise here. That's all I want to point out. So the takeaway is that we see that our created pseudo outcomes will lie in our created intervals with a probability that's greater than 1 minus alpha minus this quantity, which we'll refer to as the coverage gap. And I just want to point out that this coverage gap is a function of these weights and these total variation distances. We can think of these total variation distances as a metric which quantifies the difference between the test point and any training point in the calibration dataset. So for example, if the test point is very similar to a point that we've seen in the calibration dataset, it's going to be a very small value for the DTV, whereas if it's different from that, it's going to be a higher value for the DTV. And in the next theorem, the takeaway is basically that the true it can be shown that the true ITE coverage is greater than or equal to the pseudo outcome coverage, which we've already seen is greater than or equal to 1 minus alpha minus this coverage gap. So we are able to show that if we create intervals for these pseudo outcomes, they're going to cover the true ITE with at least as much theoretical guarantees as we can get for the pseudo outcomes. Now, as promised, I'll go into the weights and why they're important. So first, as I already said before, the coverage gap is a theoretical quantity. It's a function of weights and total variation distances between test data point and all training data points. The problem with this is that the TVDs are not observed in practice. Like before you see a data point, you don't really know what the TVD is going to be like. So the best we can do is, if I go back, to reduce this quantity, since let's assume we don't observe this part. So the best we can do is attempt to choose weights so that we reduce this quantity and get coverage closer to 1 minus alpha. So that's the best we can do in practice. And how we do that is we leverage qualitative information, which practitioners will have. And the idea is very simple. It's basically providing more weights to points similar to the test data, meaning that they have lower TVD, and lower weights to points much different than the test data with higher TVD. So essentially what we're trying to do is we're trying to assign lower weights to points that are dissimilar and higher points to similar data points from the training data.
These the quasi outcome points that you're talking about?
Yeah, so yeah. Yeah.
I have a question mainly because I haven't seen this coverage gap trick. I'm intrigued, but if you're weighting towards your test data,
Mhm.
isn't that getting rid of the separation of the three different
So
sections?
you're not weighting the test data. So you're saying that if you have test data, all the points that you have, like which of these is going to be closest or more similar to what you're going to observe. So for example, let's say you have like some sort of pilot study where you've seen that at week 5, like individuals tend to, like their outcomes tend to decline. So you would leverage that information, and when you're doing another MRT after that, you could be like, okay, at week 5, we're going to upweight points from this previous MRT, and that is going to inform how we are going to, yeah.
Oh, I see. So your underlying cohort is shifting to something more severe, so you push the
Correct.
confidence interval to be
Yeah,
similar to
exactly.
situations.
Yeah.
That's a cool idea I haven't seen.
Yeah. So that's basically the idea. Yeah. Yeah. So the choice of weights, as I've already kind of hinted at, in MRT settings, you can assume that your near future outcomes are going to be highly correlated with your current outcomes. And if as you move into the future or more into the past, those outcomes are going to have lesser and lesser of an impact or dependence. So this kind of motivates some sort of a temporarily decaying weighting scheme. I have annotated 4 different types of weighting schemes. So for example, if we are going to make a prediction interval for some person at time point 50, these are how we can weight points from our calibration dataset to create better prediction intervals. So for example, let's say we are at decision point 50, and we are trying to make a prediction interval for some person here. We can upweight points belonging to our training dataset that at decision point 50, because we can claim that is going to give us a very good representation of what this person's outcomes might look like. And that is a way of decreasing the coverage gap, essentially. So the purple flat line is basically if you apply equal weights, and these lines are different decaying, like different temporally decaying weighting schemes. And the rate of decay and the shapes will depend on the parameters that you choose. But I've just for the sake of illustration, I've just shown how 3 different decaying weighting schemes can be used to upweight points closer to the point that we're looking at. Yeah, go ahead.
So weights are applied to the training data? Or
Yeah, to the calibration data. So the weights. Yeah, so if we go further back. No, you're fine. No, I probably did not. Yeah. So here, we were calculating the 1 minus alpha quantile of V, right? So instead, if we imagine this is 1 minus alpha quantile of a weighted distribution of V's, so the weights go to the V's, which is a part of the calibration data set. So we are assigning weights to these calibration data V's, which is going to give us some sort of idea about what the true quantile might look like. Okay. Is the point. Yeah. And yeah, and I have some simulation settings where I show how it affects. Yeah. To summarize what we've talked about, like what I've talked about so far, since we don't have the exchangeability assumption, it results in some loss in coverage. The best we can do is reduce this loss in coverage, and we've provided a theoretical lower bound for this loss in coverage. As I've already alluded to, we can choose these weights more intelligently so that we can reduce this coverage gap. And the nice parts of my algorithm or method is that it's flexible to handle like any sophisticated machine learning model, and it will retain all theoretical guarantees. And finally, since from theorem 2, since we saw that the true ITE coverage will be at least as much as the pseudo outcome coverage, and based on simulations, we verified that extensively. we are going to use this idea and we're going to leverage pseudo outcome coverage as a proxy for real ITE coverage, because in real data applications, we never observe the true ITEs, so it's very hard to say if we are actually covering it or not. So before we get into simulations, I want to point out that there's two types of predictions we can be doing with our data structure. One of them is if we have a new cohort of people and we want to predict outcomes for them, that we refer to that as predicting downwards. And we can also predict outcomes for an existing group of people at future time points, and we call that predicting outwards.
Say that again, please.
Yeah, so
What's downward?
So predicting downwards, I'm just referring to this as predicting downwards. So the new test point that we're predicting for could be from a new cohort of people. So not the cohort of people that we have, but from a new cohort of people. So that's predicting downwards. And if we are predicting an existing person at a future time point, that's predicting outward. Yeah. So in the plot that we see right now, this is some simulation results that I have for a change point scenario. So what I mean by a change point is that in these vertically dotted lines that we see, we change the treatment effect to go from positive to negative. So essentially, it's going from being a beneficial treatment to like a harmful effect. This is kind of an extreme case, but it's nice to see how these weights are important. So we have two weighting schemes here. E is the equal weighting scheme, and D is one of those temporarily decaying weighting schemes. We see that at change point, if when we're predicting for a new cohort of people or predicting downwards, we see that the decaying weighting scheme is able to maintain target coverage levels throughout. And the reason is that since we are predicting downwards, we already have information from an existing, we already have information belonging to those time points from some previous cohort. And we probably saw that at this time point, it kind of dips, like the treatment effects changes. So what the decaying weights method does is that it starts increasing its interval lengths to ensure that we have valid coverage even at change point and after change point. Whereas we see that for the equal weighting method, since it's not able to do that as well as the decaying weight method because it's applying an equal weight to all observations. So it's not really relying on observations that are temporarily closer, it's treating each and every observation equally. So it's not able to attain coverage level, like it's not able to attain desired coverage levels. And this is one sort of situation where it fails. The other situation is that of model misspecification. So when we're predicting outwards, we don't really see the change point in our training data. So that's why when we go to the change point, both these methods actually fail. And the reason is that we didn't observe it in our training data, so there's no way that any weighting scheme would have predicted that would happen. But the good part about the decaying weights method is that it starts to upweight points that are closer temporally. So at the next time point itself, we can see that it goes back to attaining the coverage levels because it's giving a lot of weight to all data points at change point, whereas the equal weighting scheme is still giving equal weight to all points. So it takes a much longer time to recover, and it's basically has a converging trend towards the decaying weights method. These are simulation results for a no change point scenario. And we've considered two different outcomes, a linear outcome and a nonlinear outcome. And for models, we've considered a linear model with a lasso penalty, a neural network model, and a random forest model. Coverage refers to true ITE coverage. P-curve refers to pseudo outcome coverage, and these are the average lengths of the intervals. So we see that when we have a linear outcome, the linear model should do pretty well, and it is. The random forest does best in this case, but the linear model provides very similar performance, like competitive performance. But when we move to the nonlinear setup, we see that the random forest is performing the best, followed by the neural network, and then the linear model is, like all of them attain target coverage guarantees, but the linear model is making very wide prediction intervals. So this is basically saying that if you have better models to create your pseudo outcomes, then you have better prediction intervals in terms of length. And finally, we come to my real data example, which is based on the Intern Health Study, which is a real life MRT. So they enrolled 1,563 medical interns, and activity, sleep, and mood-related data was collected via Fitbits. And then these measurements were aggregated on the weekly level. We have mood on a scale of 1 to 10, step count in thousands, and sleep in hours and minutes. The dataset that I was given, and in their paper, they have performed these transformations. I'm not sure as to why, but this is the data that I used. So the step count, they had taken the cube root of the step count, and for sleep in minutes, they had taken the square root. And we basically provide prediction intervals for all of these outcomes separately for each intern in our testing data set and at every time point. And for missing data, we do single imputation because our method cannot handle multiple imputation yet. These are results for predicting downwards. We held out 25% of the data set for evaluation purposes. So we can see, so first I would like to point out that we don't have true ITE coverage because we never observe it. We only have pseudo outcome coverage here. And then these are the 3 outcomes that we have. And these are, we can see that irrespective of the model we use, we are able to obtain like coverage, like desired target coverage or close to it, like close to 95% coverage in each case. And in different cases, different models perform well. The linear model performs well for mood, for sleep, and then the neural network does best for step count and the mood outcomes. So to conclude, we have built prediction intervals for time-varying ITEs without the exchangeability assumption, which was one of the key limitations in prior work. We have elucidated how choosing weights intelligently can help in reducing the coverage gap. The main good part about our method is that it's flexible to use any machine learning model. And we have a few good future directions. The first one is what I'm working on right now. It's basically trying to figure out how to make these interval lengths more efficient in terms of, so one of the problems with conformal methods is that it's too conservative in the sense that it creates wide intervals and they might not be very useful in practice. So my current work is focusing on how to get intervals that make sense from a clinical or a medical standpoint. And then I'm also trying to get these conditional guarantees, which are stronger guarantees than the marginal guarantees that I just showed. The second thing is that I assumed a known propensity score throughout. What would happen if we did not know that? Now, I know that for MRTs, it's given by design, but future work could explore how an unknown propensity score would fit with our given mechanism. And once we have these intervals, it would be nice to see how these could be actually used in decision-making contexts and to create like adaptive intervention strategies. So those are the points that I wanted to make. And then I have a few key references. And yeah, that's. Yes.
I would like to hear some examples of what you say when you're going to use these. How are you going to use the intervals in this?
Yeah, so from off the top of my head, I feel like it can be used as a benefit analysis, right? So if you have, let's say, a range of values that you expect a person to have if they get the treatment, you can decide if the treatment is, if it's prudent to assign treatment or not. So it's kind of like another factor that you can use to inform your decision making in those contexts.
That helps you decide whether the treatment was effective. Is that what you're
Whether
saying?
the treatment will be effective at the future decision point. Yeah. So that's one of the things that you can do. Yeah. You could also like use features from these prediction intervals to inform like or get a better estimate of average treatment effects. So one of the main drawbacks of MRTs right now is that they have this like high dimensionality problem. So this can also be thought of as like a you're lowering the dimensionality because you just have an interval, and then how to use these features is again another interesting question. But yeah.
Swaraj.
Yes.
Thank you.
I don't know if you realize this, but we have quite a few people online from
yeah.
Andrew Ekstrom's public health statistics class. And I just thought, if I was such a student, that I would very much like to know more about this example. What were these treatments that people were being given over time? And what was the goal of, you mentioned
yeah.
a hypothetical negative treatment. I'm pretty sure you
Yeah.
never shock them through their Fitbit or anything, but
Okay.
what was the,
No, that's a very good point, and I'm sorry, I feel like I missed that when I was
Yeah,
talking
yeah.
about MRTs. So one of these examples is if you're trying to see if, when I say treatments, I feel like all our minds go to treatments that we're administering physically, but like this is, since it's in the world of mobile health or mHealth, it's more like you get a message on your phone that asks you to walk more, and then it's about analyzing if your step count increases based on that message. So mobile health is basically concerned about you getting interventions, which are basically messages or like prompts on your phone or your watch, which tell you to do certain stuff, and assessing the effectiveness of those. So when we're talking about a negative treatment, so what I considered is something very extreme. Realistically speaking, I feel like it might go from positive to zero. So for example, if we are in a trial, when we are starting the trial, we probably would be more receptive to those messages. But then after a certain point, we might be like, oh, I don't want to do this anymore. So like you have like a zero effect. So in most MRTs, there is like some decision point after which we see these effects die down. And it's because people just don't want to move forward with the trial.
and secretly, this will help me too. I'm going to act like it's for the online people, but could you go back to your pseudo observation kind of setup? And in the context of your data set, could you give some intuition about what those pseudo observations for the counterfactuals? Yeah, this formula. Can you give a little bit of a context for how this fits in with your example?
Yeah, sure. So so the pseudo outcomes that we're building, right? So let's say if we just focus on this second quantity here, this is basically the average, the conditional average outcome if treatment is equal to 1, and this is the conditional average outcome if treatment is equal to 0. So if we just focus on this, we see that this is kind of like a conditional average treatment effect, right? So what these meta learners are trying to...
Is this averaged over time? I'm thinking of these walk prompts.
Yeah, so
that they're getting, and so are these averaged over time, or are they averaged across individuals, or are they averaged across
you can do
both?
either. Like that's also one of the benefits of our method. Like you can mostly do anything, and the guarantees are still valid. So yes, that's a very good point though. Like you can have, so I have these intervals varying over time, but these estimates can vary over time, but you can also not have, like you can also just be like, I'm averaging these effects over time. That is also valid. The reason you should have good models here and you should try to do a good job is that if you have a good estimate of these pseudo outcomes, the better you estimate your pseudo outcomes, the better your intervals will be in terms of length. So you're going to have, yeah, so that's the only drawback of having poorly designed pseudo outcomes.
Mm-hmm.
Yes.
You said you estimate like y equals f of x with like neural networks for an MRT, or like a random forest for an MRT.
Mhm.
These are time, like
Mhm.
there's
Yeah, so for
time.
random, yeah, so for those, I just put time as a covariate.
Okay.
Yeah.
So when you see some of these data, do you think that this is effective? These message treatments are effective?
So these papers, personally, I believe they are, but to the extent can be debated, right? So I feel like statistically speaking, they are effective, but practically speaking, I'm not sure how effective they are right now, especially if you're conducting like a large scale trial over the course of, let's say, 4 or 5 months. It's very likely that you see non-responses after the first 2 months because people just get tired of following those prompts. And yeah, you have a lot of non-responders. And so it's very hard, but yeah, it's still an evolving area. So maybe we can.
I guess all exercise classes have that, where people
Yeah.
start out, burn out, and then
Yeah.
the ones that stick
Yeah.
with it. Yeah.
I've seen that used in, I won't go into details because they're not important, but someone used a program to help people not go back to prison. One of the pharmacy program was to get a hold of a job.
To get hold of a job, I see.
Yeah, it's the strongest predictor of not going to prison.
Mhm.
So they required, pretty much close to requiring an outcome.
Getting a job is hard to do after you've been out of prison.
True.
Very hard to do.
That's the point. It's like you're requiring something that's pretty close to a particular outcome to successfully complete. You're taking the effect, grabbing a bunch of it, stick it in your cause.
Yeah.
All right, I think if there's.
So I think this is super interesting. I know I've learned a few different,
Online,
Oh, okay.
can we ask,
oh, yes, thank you.
can you read that?
Yeah, sure. So
If there is. no-
if there is no positive result for certain types of people after treatment, would we want to give them the treatment in the first place?
How do you know that?
So I think it's a really good question because we do a lot of studies where we're not sure whether the treatment will be helpful at all. We're doing the study to understand that better. And actually, I think only 30% of all studies that start answering these questions end up moving forward because, you don't see a benefit. So absolutely, if you do an analysis and there's just no positive result, we tend to not put that through. And that said, if it's a treatment where you could have side effects like a pharmaceutical, that's
Yeah, that's a different.
quite,
That's a different field. Of,
yeah, that's quite, you know,
that would be unethical at that point.
yeah,
Pre-randomized
right. If
experiment,
you're
yeah.
telling them to walk more, maybe you're hurting their mental health if they feel guilty because they didn't do what they were asked to do. But I suppose that you collect data on that as well and try to understand if on multiple levels, is this helping them walk more, but is it making them feel better? Is it improving their mood? And until you collect that data, you don't have an answer for the general public. So I think it's a very good question. That's why we're collecting and trying to understand the data in the first place. Oh, Malcolm.
I just have a quick question about the assumption of a known propensity score. So typically we'd assume a known propensity score, and it would be a problem to try to estimate it because we would be estimating the propensity score in the same data that we're fitting the final model. But in this case, you already have a holdout set of data, right, to estimate your conditional mean outcomes. So I'm just wondering why it's like, why you even need to make this assumption? Like, why can't you just estimate the propensity score using that first holdout set for your nuisance parameters?
Yes, so you could, but the doubly robust learner relies kind of on either the models being correctly specified or the propensity score being correctly specified. So if by design our motivating setting just has the propensity score known by design, like it's just so much easier to just, use it. But you're right, you could, yeah. The theory also kind of relies on the propensity score being known. So we can give approximate guarantees if the propensity score is not known, but we could not give like proper, exact guarantees without propensity score being known.
Maybe like in an MRT, aren't you assuming you know what a propensity is?
Yeah.
You have those.
Yeah, his question was, even if you have those, why don't you estimate it? Because you have a separate holdout set. So yeah.
So for this doubly robust learner, which by the way, I hadn't known about, so you assumed a lot of us knew about this thing. So the noise if you don't observe the counterfactual, I mean, you're kind of imputing this difference in the means, right? Without extra noise.
Mhm.
I would have guessed that you needed some more noise there.
So the noise, so that the conformal inference framework basically tries to get an estimate of the noise after, right? So you're
Based on the
the
third.
V's, yeah.
Uh,
So you're right in a way that if your pseudo outcomes are poorly estimated, then you have wider intervals, and if you have better estimates, then you have shorter intervals.
yeah. Okay, I'm gonna figure this out eventually. I'll bug you later.
Okay.
Other questions? Otherwise, for those who attend in person, there might be pizza.
There's lots.
And so for those who
Thank
signed in, so sorry. I'm so happy that you all came and I hope you come again next time.
Yes. Thanks again. Stop
Oh, I need to stop recording.